All right, so I think now kind of seems like a good time to start, mostly because I'm all settled in. Um, so thank you everyone for joining today. My name is Nathan. I am one of the marketing managers here at Data Science Dojo. Um, and and Robert, it's an hour early. All Data Science Dojo's webinars play 1 hour too early in Arizona. I'm sorry, Robert. I think that's just a time zone thing, right? Maybe we can do 1 hour later, like at 1 o'clock Pacific sometime, and then it will be the perfect time. Um, anyways, thank you all for joining today. We're really excited to be having this crash course on naive Bayes classification with our presenter Kevin. And Kevin is the chief statistician, data scientist, and senior research fellow at the Heritage Foundation Center for Data Analysis, which is a mouthful to say, Kevin. So just a couple quick things for Q&A today. We're going to be using the Q&A tab like we normally do. So if you have a question and you're on Zoom, go ahead and post that question in the Q&A tab. If it requires kind of a shorter, quick response, Kevin's going to answer it kind of as we go. But if it's something that's going to take a little longer, we're going to save those and answer them at the end. Or Kevin's final slide, he has some ways to get in touch with him. You can get in touch with him with your question. He'll do his best to get back to you. This webinar is going to be slightly longer than our normal ones. Normally we do these for about an hour. This one may go up to 1 hour and 30 minutes. So if you have to leave early and drop off because of work or some other prior engagement, feel free to do so. We will have a recording of this, and we'll have this be able to share the slides and everything as well. So stick with us if you can. If not, we're happy to have you while we have you, and feel free to jump off. If you're on one of our live streams, I have posted the Zoom link. If you want to join us on Zoom, I'll post it again here in a minute. But if you have questions, feel free to post them in the chat. I'm going to do my best to bring them onto Zoom with us so that you can have your questions answered as well. And with that, so Kevin, why don't you go ahead and get started, share your screen, and then we'll get going here.
Okay. Thank you, Nathan. My name is Kevin Dayaratna. I am the chief statistician, data scientist, and senior research fellow at the Heritage Foundation, Washington, D.C. So I'm going to talk, and I will share my screen. Let's see here. Let's do this. About a crash course on naive Bayes classification. There are various types of problems that we might be interested in as statisticians and data scientists, namely making new product recommendations, predicting political affiliations, predicting medical conditions, among many others. In the realm of predictive modeling, these are a variety of questions, and as well as many more, that can be answered using the techniques that we're going to talk about today. And we're going to get to specific examples of these things later on in today's webinar. So first, I'm going to do a very, very brief probability refresher. And if you don't have any probability or stats background, that's perfectly fine. I'm going to talk about the basics that we need for this. And then I'm going to get into an introduction to naive Bayes modeling, both from a theoretical perspective and a coding perspective. The coding that we're going to do today will be in the R programming language. So feel free to download that if you don't have it. And the codes will be made available to you, so you'll be more than welcome to utilize them. So I'm first going to talk about a probability refresher. So probability is a concept that enables us to quantify how likely certain events are to occur, such as, like in terms of a random experiment where you have different potential outcomes for something, such as, for example, tossing a coin, rolling a die, tossing a coin, heads or tails, rolling a die, what side will it land on, 1 through 6. There are a variety of outcomes, and those are the outcomes, say, for example, rolling a die 1 through 6, that you can end up with. And the idea of probability is to quantify how likely some of these outcomes or all of these outcomes are to occur. So the basics. So I've taught probability and statistics for many years. The idea is when students come in, they typically quantify, before we have our course, how likely certain events are to occur with percentages between 0 and 100. Probability is the same idea, but the endpoints are 0 and 1. 0 is no chance that the event will occur. 0.5 is the event is just as likely as it is unlikely. And 1 is the event that the event will occur with certainty, or 100% chance. So probabilities quantify likelihood of something occurring between 0 and 1. Now, there are, excuse me, there are a variety of ways we can assign probabilities. We typically speak about the probability of an event, say event A occurring, for example, going back to the example about rolling a die, 1 through 6. The probability of the die landing on 6 occurring, or 1 occurring, I should say, or 6 for that matter, is defined as the number of ways that event can occur over the total number of outcomes. So in that case, the probability would simply be 1 out of 6. There are two main ways that people conceive of probabilities. One is through a relative frequency, and the latter is subjectively. Let me talk about the relative frequency concept, because that's basically what we're going to be using here, although the concept of naive Bayes touches on subjectivity as well. Suppose you have a coin and you toss it 10,000 times. Roughly speaking, 5,000 of those will be heads. And the idea is that in this sense, probabilities would quantify a long-run frequency based on a random experiment. Subjective probability is, like the term says, more subjective or opinion-based. Sometimes you don't have the luxury of engaging in these long-run experiments to generate a long-run frequency. For example, what is the chance that it will rain tomorrow? And Nathan and I were just talking about rain in, say, Seattle. The probability of that, you can't have a million tomorrows to sample from. So you would use other techniques to subjectively assign the probability. And when you turn on, say, the Weather Channel, you will hear there is maybe a 30% chance of it raining tomorrow. So excuse me, for any event A, P of A right here is denoted as the probability that the event A occurs, and that's between 0 and 1. S is known as the sample space, or the set of all possible outcomes. It is also sometimes denoted by omega, the Greek letter. So here's an example. You have an example here's an example of a bag with 10 balls. 1 is labeled 5, 2 are labeled 6, 3 are labeled 7, 4 are labeled 8. And let's let A be the event that a chosen ball is labeled less than 7. So what I'm going to do is I will tell you how we would compute this, because this is just a very basic example that I want us to get a hold of. So P of A equals, so you go to the slide here. 1 is labeled 5, 2 are labeled 6, 3 are labeled 7, and 4 are labeled 8. So you have 10 possible balls, but 1 and 2 are 5 and 6, excuse me, are both less than 7. So the probability of, now in the concept of probability, we have an event A, and the sample space consists of all possible events. So, and this comes up in naive Bayes modeling, the probability of the sample space is 1. So the probability of a bar, or the complement of an event, the opposite of that event occurring, for example, not rolling a 6, choosing a ball that is greater than 7 or greater than or equal to 7 would be the opposite event occurring, and that's just 1 minus that associated probability. Now, we have the probability. We talk about the events, probabilities of events occurring in terms of these set theoretic notations here. The probability of A union B is the probability of A or B occurring. That's how this is read. And you could visualize it this way. And this is what we get involved in with naive Bayes modeling, the probability of 2 events occurring, P of A and B, and that is the intersection of 2 events. Now, the joint probability is one way that we define the probability of A and B, that the probability of 2 events occurring together or multiple events occurring together is known as a joint probability. A marginal probability is the probability of A or B, or a single probability.
Hey, Kevin.
Yes.
Sorry, are you meaning to be sharing your slides right now?
I'm not. Oh, I'm sorry. I thought I started sharing it again. No? Okay, thank you. Let's do that. I thought I did that. Sorry about that. Okay, we'll go back here. So let's go over this real quick. These are the slides I went over. So the complement of an event, this is visual representation of what I was referring to earlier. That's basically everything that is not the event. The sample space consists of the event and everything outside of it. So if we're interested in the complement, P of A bar, that would be 1 minus probability of A. Now, we're interested in events, probabilities of different events occurring, A union B, that is the probability of A and B occurring. And you could visualize it this way. The probability of A intersect B, that is, or probability of A and B, that is the probability that two events are occurring together. And that is also known as a joint probability, the probability of A and B. The marginal probability is the probability of a single probability occurring, like probability of a single event occurring, I should say, probability of A or the probability of B. Now, here is some hypothetical data about STEM majors finding employment. And the reason I include this is just purely for illustrative purposes. The probability of a STEM major who, so this is survey data, quote unquote data, I should say, amongst respondents. And you can see here that 3% of the students surveyed were STEM majors who did not find employment within 6 months after graduating. 17% of them were non-STEM majors who didn't find employment 6 months after graduating. 56% were STEM majors who found employment within 6 months after graduating. And 24% were non-STEM majors who found employment within 6 months after graduating. And using the concept of relative frequency probability, one could interpret this as saying, assuming the data is representative of the general student population, the probability of a randomly chosen person being a STEM major and not finding employment within 6 months after graduating is 0.03, or 0.56 for being a STEM major and finding employment within 6 months after graduating, and so forth. So in a nutshell, these are joint probabilities, and you can see when you add them across the columns, they are marginal probabilities. 0.2, 0.8, for example, of those who don't find employment within 6 months after graduating, that probability is 0.2. 0.8 is the probability of finding employment within 6 months after graduating. And you have these probabilities of being a STEM major and not being a STEM major amongst randomly chosen individuals. This concept is something we directly use in naive Bayes. That is called conditional probability. That is the probability that A occurs given that B has already occurred. For example, assuming somebody is a STEM major, what is the probability that they find employment within 6 months after graduating? Well, this is the definition. The probability of A and B, this joint probability divided by this marginal probability. And in this case, it is 0.56, the probability of finding employment and being a STEM major, divided by 0.59, the marginal probability of being a STEM major. And that comes out to 0.95. So what does that tell us? There is a 95% chance that given someone is a STEM major, they find employment within 6 months after graduating. Now, two events are statistically independent. This concept comes into naive Bayes if and only if the probability of A and B decomposes into the products of the individual probabilities. And another way of saying this is that the probability of A given B does not depend on B and is purely the probability of A. And same for probability of B given A. And if you have dependent events, then you can decompose the definition of joint probabilities this way in terms of the product of the conditional probability and the marginal probability to get this joint probability. So now that is all the probability theory that I wanted to share before getting to naive Bayes. So before we go on, does anybody have any questions? Nope. Okay. So suppose we are shopping at the grocery store. And we, with technology these days, we can equip sophisticated equipment to grocery carts that could have information about where you're from and provide direct product recommendations. So here's a simple example. Can conditional probabilities shed light on how likely a customer is to purchase a grocery product given known information? So here are some data. This is from this book, I believe it's titled The Ancient Art of Numerati. It is available online. And shoot me an email. Afterwards, my email address is in the slides if you'd like a link to it. Here is some hypothetical data about customer purchase behavior. And you have the zip code, whether they bought organic produce and whether they bought Sencha green tea amongst 10 customers. Here are some good questions. Suppose, what is the probability that a particular event D will be observed? That is, what is the probability that customers who showed up belong to the zip code 88005? That is, what is the probability of the event A 88005 occurring? And what is the probability that a particular event D holds a given hypothesis? That is, say, for example, what is the probability that a given a particular customer purchased Sencha tea that they were from zip code 88005? So the first one is very easy to do. 88005. So there are 10 customers. How many are from the zip code? 1, 2, 3, 4, 5. So we have, I will here, 5 out of 10. All right, P of 88005. Right? Now, this question is a more interesting question, at least to me. What is the probability that given that they purchase Sencha tea, that they will be from zip code 88005? So we can compute that using a definition of conditional probability. That is done on the following slide. The probability of being in zip code 88005 and purchasing Sencha tea all over the probability of purchasing Sencha tea. So what is this probability, being in 88005 and purchasing Sencha tea? Well, we go back to the slide here, from current slide. So how many purchased Sencha tea and were from the zip code? We got 1 right here. This doesn't qualify. This does. And so does this. So we have customers 1, 3, and 9. I'm sorry. 1, 6, and 9. So 3 out of 10. So as you can see here, the probability is 3 out of 10 divided by 5 out of 10, which is 3/5 or 0.6. Okay. Does that make sense? So we would be interested in conditional probabilities of purchase intent. That is, what is the probability that a customer buys Sencha tea given that they are from a zip code? And what's the probability that they don't buy Sencha tea given that they are from a zip code? For example, you walk into a grocery store, you have your shopping cart, and it is a sophisticated shopping cart where you can actually enter in your locality, where you're from. You put that in. Then you could think about how to target ads. So I'm not going to go into the details here, but you can compute these using the techniques we just talked about. The probability of purchasing Sencha tea and belonging to zip code 88005 over the probability of belonging to 88005 is this conditional probability of purchasing Sencha tea given that you're from the zip code, and that comes out to also be 0.6. The probability of not purchasing Sencha tea given you're from the zip code comes out to be 0.4. So you compare the two. The probability of purchasing Sencha tea is given that you're from the zip code is 0.6. The probability of not is that you purchasing this Sencha tea being from the zip code is 0.4. So they are more likely to buy than not. So therefore, it's worth considering posting ads to people from the zip code, or in the shopping cart, for example, providing specific ads to guide them to particular areas of the store. Now, I'm actually going to backtrack a little bit here because there is a very, very useful way to consider conditional probabilities. And this is very useful if you, when you consider the definition and the context of conditional probabilities, and this is discussed in more advanced probability textbooks. Suppose you want the probability of purchasing Sencha tea given that you belong to zip code 88005. We showed how this can be computed right here. Another way to do this is to just look at the zip code 88005. How many are there here? 1, 2, 3, 4, 5. We counted this before. Amongst these, how many purchased Centra T? Excuse me. 1, 2, 2, 3. So that is another way you can get to this answer, 3 out of 5. And I'll leave it as an exercise to you to do the same thing here, but you will be able to do the same thing with that probability. Okay. So now suppose we'd like to know how likely it is that a person from this zip code 88005 has bought organic produce and will purchase T, then not. This involves a new technique known as Bayes' theorem. This work was published by the Reverend Thomas Bayes a couple hundred years ago, and it was done posthumously, I believe. This is Bayes' theorem. Essentially, the idea with Bayes' theorem is that it enables us to flip conditional probabilities. We may have the probability of B given A, but we need A given B. Bayes' theorem is as follows. The probability of B given A equals the probability of A given B times the probability of B, all of the probability of A. You can derive this using definitions we talked about. This is done in most standard probability and statistics textbooks. Excuse me, the probability of A and the probability of B are referred to as prior probabilities. And this probability, the probability of B given A, is a posterior probability. Now, suppose we have multiple statistically independent events, A1 through AN, and we like to compute the probability of given B, all such events, the probability of B given all such events, A1 through AN occur. Then this tweak to Bayes' rule would be as follows, where you take the product of all these conditional probabilities, multiply it by this marginal probability of B, and divide it by the joint probability of A1 through AN. And this is what we utilize for naive Bayes modeling. And if we want to compare the probabilities of different hypotheses, H1 through HM, we would do that as follows, by computing these different posterior probabilities. But you notice something with these equations. Notice that the denominator is the same. So why should we bother to compute it if we keep dividing by this exact same thing? What we can do instead, probability is proportional to this product times the prior probability of the hypothesis in question. And I know that's a lot of statistical jargon, but we can get to it. We can do an example of that here in terms of what I had just talked about. Suppose, for example, we'd like to know how likely it is a person from the 88005 zip code who has bought organic produce will purchase T than not. Probability of H1 given D is the probability of purchasing Centra T given they are from this zip code and they have purchased organic produce, and the competing probability is not doing so, given the same information. So given what we have discussed in the previous slides, this is just the product of belonging to the zip code, given that they purchase Centra T, purchasing organic products, given they purchase Centra T, times the marginal probability of purchasing Centra T. And you can compute these. I'm not sure we want to spend time going into calculating all of these, but we did the first one already, 0.6. 0.8 is the probability of purchasing organic products given that you purchased Centra T. And 0.5, which we calculated, is the marginal probability of purchasing Centra T. This comes out to be 0.24. Now, this posterior probability of not purchasing Centra T is proportional to the following, and it comes out to be 0.05. So you can, what does this tell us? Well, you can compare the two, and it is more likely that somebody from this zip code who has purchased organic produce will buy the Centra T than not. So let's post the ad for the customers. Okay. Yes, there will be, there are no links yet, but there will be, and the recording will be shared. Yes, so don't worry about that. Welcome. Okay, so now, okay. Before I go on, stop this. I'm just gonna stop sharing so we can see. I just wanted to touch base because now we're going to get into some naive Bayes modeling and coding. Are there any questions? Okay. What I will do is I might as well just share it right now. Have it right here. Oopsie, sorry about that. Sense Dojo codes. I will give you all a link to the R codes that we'll be using, and you can run them in RStudio or in RStudio. This zip file should have everything, and we will get to them in a bit. Are there? Okay, so I assume there are no questions. Okay, so let's go on. I made this mistake last time. We're not going to do it again. Share the screen.
Hey, Kevin, before you get started, it looks
Yes.
like Steve did ask a question.
Oh, I'm sorry.
If that's it came in right as you were getting started.
I just missed that. I don't think I see the question. Is it in the chat?
In the Q&A tab.
Oh, okay. I was looking at the chat. Sorry. Good question. What is the probability that they will buy the second time when they return? I would have to think about that because I think you would want data on multiple visits to do that. But that is a great question. I have done some work on this type of thing when I was in graduate school in the past, in particular, looking at multiple purchase occasions and modeling things like price sensitivity, taking into consideration past prices. This is a concept called a reference price, where you have in your head, for example, when you go to the grocery store and you buy orange juice, you'll have the price you paid, say, 2-3 weeks ago when you purchased your orange juice before. Naive Bayes, so Gabriel's question, naive Bayes can be calculated only considering two facts, the probability for, I'm sorry, or is it possible to have two? I'm sorry, I'm not quite understanding the question, Gabriel. Can you clarify? Okay, sure. Oh, well, that's Steve's response. Gabriel, if you want to clarify that, please do so, and then we can talk. So Parsa asked a question, can you do this in Python? The answer is naive Bayes modeling can, of course, be done in Python, but my codes are R codes, so they cannot be done in Python. But as an exercise, I do encourage you to translate them to Python. Sure. So, yeah, I will need a clarification of your question, Gabriel, but we can we get to that, and I'm happy to talk afterwards. So, is there another one? Yeah, okay, and I see the question here. Okay, so naive Bayes, can it be calculated only considering two facts, the probability for a third one? Yes, there is a concept called multinomial naive Bayes, and given the time we have, I do not want to spend time getting into it, but there are ways to use these methods for multiple outcomes. This can be tweaked. This is only the beginning. Again, this is a crash course on the topic, but yes, this can be extended in a variety of ways to handle more than one outcome. Does that answer your question? Okay. So is that it? Okay. So let's move on to the actual naive Bayes modeling, and I hope I've given you a good sense of the techniques involved. Okay, here we go. Okay, I'm going to share the screen again. Where is it? So, okay, we went through all of this. Let's see here. Okay, here's a simple application. This is one of the applications I had alluded to earlier in the talk. Can naive Bayes be used to provide new product recommendations for Fitbits? This is an example from the ancient art of numerology. Eye Health 100 and Eye Health 500, these are different types of devices you could put on your wrist that measure stuff about your circulation in your heart and so forth. So here's the task. We would like to devise, what if we want to devise a recommendation system for customers and you ask them to fill out a questionnaire? What is your main reason for participating in an exercise program? Health, appearance, or both? What is your exercise level? Do you sit at home? Do you engage in moderate exercise, or do you engage in active exercise? What is your motivational level? Moderate or aggressive? I guess they don't bother asking people who aren't motivated because they're not going to do anything. And are you comfortable with tech devices? Yes or no? So here is this data regarding what these hypothetical customers filled out. I-100 for the I-100 and I-500. And this can be used as the basis for constructing a naive Bayes model. So we got a coding example in R, and we can develop a recommendation to decide which Fitbits to suggest to customers. Let me first go into the theory here. So how would we use naive Bayes to recommend a model for a person whose main interest is health? Their current exercise level is moderate. They are moderately motivated and are comfortable with tech devices. So these are the two competing probabilities that you would need to compute. I-100 given that information and I-500 given that information. And you can compute these two probabilities accordingly. You know what? Let me say this. I've actually mentioned this when I've taught this at universities. I'm not the biggest fan of how these probabilities are actually constructed because, like you could see here, I don't use the term equals. I use proportional. And the reason is, you go back here, we have dropped the denominator because the denominator is the same. So they're proportional. So you are not really computing a probability per se, but it is a heuristic for a probability. The value you are computing is proportional to the probability. And it at least tells you something because then you can compare the different numbers that you are getting. So anyway, you have this here and we can compute it. And this is how you would compute it. You compute the probability of health being the priority given that they've chosen this, this conditional probability, this posterior probability, I-100 given this information. The probability of health being their priority given that they've chosen the I-100. That they engage in moderate exercise, the probability that they engage in moderate exercise given that they've chosen the I-100, motivation, being comfortable with tech devices, and so forth, of course, times the marginal probability. And analogously for the I-500. So you know what, I don't want to leave everything to you guys to compute, but we'll go through, one or two of them. What is the probability that given that they chose I-100, health is their priority? Well, we can go back. So 1, 2, 3, 4, 5, 6. There are 6 I-100s. Let's double check that. 1, 2, 3, 4, 5, 6. There are 6 customers who've chosen the I-100. Amongst these, which is health their priority? This is the alternative way I suggested that you could compute conditional probabilities, and it's easier. There is boom, just 1. So that probability is 1/6. And you can compute these other probabilities as well. So you multiply them together, and your posterior probability is proportional to 0.00309. Analogously, you can do the same for the I-500, and your posterior probability is proportional to 0.01975. So the I-500 posterior probability is greater than the I-100 posterior probability. So therefore, you would recommend the I-500 to people whose main interest is health, whose current exercise is moderate, they have moderate motivation, and are comfortable with tech devices. Any questions? Because now I'm going to open up the R code that does this. Oh, okay. So let's do that. I will share the screen. Now this time we want to share RStudio. So these are the codes for the examples. Let's go to this one here. Excuse me. So let's do this. So I will walk through this with you. This is the classifier. This is a function in R that takes into account the interest, exercise, motivation, comfort level. And it loads the data which I provided to you via CSV file. I will load this for you so you could see it. Yep. Let's do this right now. So here is the data. This is what I want to show you. You can see I just put this into a CSV file, which can be developed, which can be constructed in Excel, and then you can load it into R using the read.csv function. Sorry, this is the wrong one. Where is it? And we tagged on the titles here, so you can see this. Let's bring this here actually, so it's easier to see. So then what do? We find the unique model numbers. There are two here, I-100 and I-500. This extracts them. And what we do is we compute a matrix of probabilities that pertain to the various conditional probabilities that need to go in our naive Bayes model. This initializes it. And we fill this matrix one by one, going through val, which is the number of unique models. And we subset the data based on each model, and then we compute the probabilities here. That is done right here. And this goes on for up to one less than the dimension of the matrix, because at the very end of this, we tag on the marginal probabilities, which we need. And boom, we compute the product of those probabilities, which we did in the slides, and output the results. And I encourage you to play with these codes, tweak them, do what you need to with them. And here is an example of this in action. So I will run this again. And here we load the data and the classifier. And then I have an example here. Here is a person whose interest is health. They are moderately motivated. This is exactly what we did in the example. They engage in moderate exercise. They are moderately motivated. Their comfort level is yes. I can run that right here. And as I run that, you can see the probabilities associated with the I-100 and the I-500. The final vectors are this final vector is the choices of the two probabilities. And then this line right here in my code, which.max computed the maximum value from this vector, and that was I-500. Well, it computes it finds a maximum value and then finds the associated device, which is I-500, which is what we found in the slides. Here are two more examples. Suppose somebody's interest is both health and appearance. They actively engage in exercise. Their motivation is aggressive. And they are comfortable with devices. We can compute that. Control Enter, X2. And I can look at the results here. Here are those probabilities. And again, this person is also suggested to have the I-500 device. And again, right here is another example. This person denotes interest as their, appearance as their interest. They are more sedentary. They are moderately motivated, but they are also comfortable with tech devices. And you can see here, you run it. And in this case, you have the probabilities here, the final probabilities, and this time the I-100 wins, and that is a recommended product. Okay, I see some questions here. Let's see what they are. Okay. We will okay, so Robert had a question. I am currently working in Python. I have no experience in R just yet. At your convenience, can you recommend a resource for teaching and demonstrating such models in Python? Yes. I will type my email in the chat and I will send you a book. So here's the thing, though, with this, Robert. I mean, these models can be written in any language that you want. So I just wrote these from scratch in R. They can be done in Python, but you would typically, I mean, one would have to write the models from scratch there. So, but I think maybe what you're getting at is, are there books that have that basically provide the presentation in Python? And there are some. Let me look into it. Shoot me an email, and then I'm happy to answer that. And Kaushik had a question: how does naive Bayes take care of noise? And the answer to that is a very good question. And we will get back to questions along those lines at the very end of the talk. So hold that thought. But yes, you touch on a very good point that we are making a pretty big assumption about statistical independence. And that's why they call it naive Bayes, but it's not necessarily that naive. Let's put it that way. Okay. So, all right. Are there any, okay, so then parse out another question. I get figured, but so I'm sorry. So I mean, you could just run this in RStudio, and when I just ran each of these, I'll share my screen again. Parse out a question: how did I run these in R? What I did was, you can just hit Control Enter in RStudio, and it will run things line by line. And that's what I did. And this iHealth classifier code that I first presented to you, that is invoked in iHealth_NB, which you should have. And that is the classifier model. Okay, I'm happy to share the slides as well, but you should have the codes already. Okay. Okay, is there another question? Would this, says a question, would the same technique be appropriate for teasing out what is the primary motivator for purchases of the I-100? Yes. That's a good question, quite possibly. I never thought of that. But one thing you could do, Robert, is play with this data, and now you have it, and look at that. But yeah, you could train you can use those potential motivating variables as your outcome variable and see what the model tells you. Okay. Any other questions? Are more questions coming in? Okay. Yes, Chris, and thank you, by the way. Yes, the answer is yes. You can classify each customer individually, and you will see more of that in the next. This was a very simple example. We are going to ramp up the complexity pretty quickly. The next example is not going to be regarding a customer purchase behavior, though. It is going to be regarding political science, but that's okay because it's useful to see a variety of different applications here. So let me share again. We're going to go back to the slides. So we need to. Okay. Let's see. So here is another simple application: congressional voting. Can these models be used to predict how lawmakers may vote? And I think I've thought about this. This could be very useful, for example, at not just nationally, but at state and local levels as well as in other countries. So here is an example. Suppose we have prior data on votes by members of Congress and can compute percentages accordingly. The Cyber Intelligence Sharing and Protection Act, Reader Privacy Act, Internet Sales Tax, and Internet Snooping Bill. This is an example from that book I was referring to. And here is that data. You got 100 members per party, and these are the number of people that voted yes in each party. For CISPA, 99 Republicans voted yes. For the Reader Privacy Act, 1 did. Internet Sales Tax, 99 did. Internet Snooping Bill, 50 did. You can see correspondingly for the Democrats. So let's convert these to probabilities, which you could do here just by dividing by 100. And now the question is, suppose you take somebody else and they voted no on CISPA, yes on the Reader Privacy Act, no on the Internet Sales Tax, and no on the Internet Snooping Bill. What party do they belong to? Well, what you can do is you can compute the probability of voting no, given that they belong to each party, for each bill, for CISPA, the probability of voting for the Reader Privacy Act, given that they belong to each party, the probability of voting no on, what is this one called again? The Internet Sales Tax, excuse me, given they belong to each party, and the marginal probability of each party. And then this is the naive Bayes probability estimate, the product of all these together. And as you could see, in this case, 0.48 is greater than 5 times 10 to the negative 7. And as a result, in this case, the Democrat wins. So this is a very simple example. And note that it wasn't so simple as to just multiply these probabilities together. You had to take into account how they voted. The person voted no, and you have the probability of yes here. So this is not 0.99 you're multiplying by 0.01. And in this case, you're not multiplying by 0.01, you're multiplying by 0.99. Now, here's the thing though. This is starting to look like a very, very useful tool. But things don't always pan out so nicely in the real world when you are engaging in statistical modeling and data science. Let's bring into the picture another bill, the Internet Snooping Bill. And you notice that in this case, if the person voted no on it, and you want to include that in your naive Bayes modeling, if no Democrats have voted no on it, then you have a 0 probability here. That knocks the previous probability from 0.48 down to 0. Excuse me. So in this case, the Republican wins. So this is the problem here, right? Because probabilities are estimates. This is like the relative frequency concept that I was alluding to at the beginning of the talk. Just because something has been some way in the past doesn't mean it's always going to remain that way. These probabilities estimate, but they don't necessarily reflect reality. And in many cases, it's impractical to sample an entire population. How, for example, are you going to sample? I mean, in Congress, it's one thing, but how, for example, are you going to sample the entire American population? Or, for example, even sample every single customer that goes to a particular store? You have nice records, actually, for people who use, credit cards and stuff like that, or loyalty cards, but what if they use cash, for example? And in many cases, even if you can't do so indefinitely. So there may come a time when a Democrat actually votes yes for the Internet Snooping Bill. So what do we do in situations like this? The answer is we move away from the standard frequentist probability definition. We tweak it slightly with what we refer to as a Laplacian correction. And there are, some questions coming in. Oh, thank you. Anyway, thought those questions, but I'm happy to chat further about these things. So anyway, you got the standard frequentist probability, and then you got your Laplacian correction, which we've tweaked it slightly. So what have we added to this equation? M is known as the equivalent sample size, and in this case is the number of attributes a value may take, which in this case is just 2. P is an a priori specified estimate of the probability. Many people chose 1/2 just to be even-handed. And you'll notice that the probabilities, if you do this, for example, for CISPA, what you'll do is you'll just basically compute the probabilities the same way, but in the numerator, you'll add 2 times 0.5, and the denominator, you'll just add 2. So instead of 0.01 and 0.99, you'll have these quantities instead. So they change slightly. That's not a big deal. But what is a big deal is you knock out this 0 here with the internet snooping bill, where it becomes a small, very small, but albeit non-zero probability. And in this case, with this correction, the predicted member is a Democrat. Okay. So now we're going to do another coding example, and this involves much more than the last one did, but I have the code written for you. So we will develop an algorithm. Well, we've already developed it, but I'm going to show it to you to predict what party of Congress a member belongs to based on their voting record. And there is this concept. So I've stayed away from this so far in the lecture, but we're going to have to talk about it. Just because I've noticed this all the time, especially with models that are in the real world or used by the government. Just because you have a model doesn't necessarily mean it reflects reality. It could be trash because it could have no predictive validity. So what we do is, and I'll type this in the chat for everybody, we have training and test samples. And the idea is that we may take, say, 70% of our data and use that as our subdata to develop our probabilities, and then see how accurately does the model actually predict the remaining 30% of the data. So the 70% of our data would be our training sample, and the 30% would be our test sample. And then you could actually compute like a percentage, and I've done that for you in the codes, of correctness, of accuracy. Okay. So I see some questions coming in here. Let me see what they are. Yes. So, okay. Gabriel, very good question. I've only used classification features in my explanation. Is it possible to use numeric features? Hold that thought. We're going to get to that in a bit, and that's why I wanted to go till 3:30. Varis Seith had a question. Can we quantify the uncertainty in the predictions we were making? Yes, and that is precisely what I'm getting at with the training and test samples. You can quantify the accuracy of your model with testing the validity on your test sample. And we're going to do that in a second. So let me share my screen. Where is it? Yes, here's the code. Okay, so now I'm trying to share this. Here we go, voting model. And okay, we will bring this over here to this side. So we have all these codes together. Oopsie. Okay, so this is the model for this data. Now let me, how should I do this? You know what, before we get into this, let me actually show you all the data itself. Codes, voting. So this voting data is much more extensive than this simple example we had just talked about. Let's let it load. If not, I can show it to you in R, but it might be easier to see in Excel. I don't know why that's taking so long. All right, I'll give another. Okay, now we got it. No? Okay. Here, let's just do it here. I don't want to waste time. Okay, so. Oh, is it loaded? No, it's still not loaded. It's ridiculous. Oh, maybe it is. Here. I'll show it to you here. Okay. Here is the data, the voting data. See, right here. You can see in your data browser in R, but it's also open in Excel. Hopefully your Excel loads faster than mine did. And it is right here. Okay, I only have to wait for that now that we have this. Okay, here we go. All right, we'll just go through this. So what you have here is votes on a variety of bills. You have the political party votes on a variety of bills regarding, say, handicapped infants, water project cost sharing, the adoption of the budget resolution, physician fee freezes, and so forth. You have all these bills here and whether or not they voted yes or no. And you have 233 observations. So let's do this. In my R code, we have denoted 60% of the data to be the training sample, and we're going to compare the accuracy for the remaining data. And this line here extracts your training sample from your data set. And here we subset the data by party. Here are the Democrats. We look at them first. And you compute this probability matrix, again, like I did earlier, to allocate your probability, your conditional probabilities. And here we do so for the Democrats. This loop goes through the data. I encourage you to look at this in your time. I don't want to spend too much time on this in the interest of time. That computes the probabilities of yes votes. Engaging in this Laplacian correction, you can see m times p all over in the numerator and m in the denominator. Do the same for the Republican Party. We again tag on the marginal probabilities, the number of Democrats over the dimension of the training data, the number of Republicans over the size of the training data. And then we compute our test data, which is from the training sample onwards, the end of the training sample onwards, I should say. And we have a function that we invoke to actually do this, in particular to assign, to make the assignments, and that is right here, where it takes into its realm the voting of a particular line of the data set, test vec, and it takes the naive Bayes probabilities in, and then it computes a probability test matrix. If the person voted yes, you use that probability. If they didn't vote yes, you take 1 minus that probability for both parties. You multiply them together, and again, you extract out which one wins, and that is returned here. So I will run through this right now. And at the very end of this, let me tell you, we compute, and this is, I think, what the question was, the percent accuracy right here. Percent accuracy is, what we are doing is we take the assigned votes, which are coming from, the model right here. At the end, you are outputting the probabilities and the assigned party from the classifier. And you take the assigned votes and you line them up against the actual votes. And this percent accuracy compares the two. At the very end, it prints out this percent accuracy. So we could run this right now. And based on a 60% training sample, that's what I had, right? We have a 90% accuracy. So this shows that this model is pretty damn accurate. It's reasonable. It's not 100%, but it's reasonable with 60% of the data. What happens if you ramp that up to 80%? %95. So now that's fine. That tells us the validity of the model. But what if we want to see, for example, how this model engages in predictions? Here is an example. I have this other example, voting example.r, and you have the codes as well. Here is a hypothetical member, and I just made up this data. They voted yes on this bill, handicapped infants, no on the water project cost sharing bill, and so forth. What party does this model think that they belong to? Well, this takes my classifier function, voting model function, and puts in this example data and the probability matrix that was already computed. And we can see these are the two probabilities, and this is the assigned party, the Democrats. So this voting behavior is predicted by the model to be a Democrat. And again, I encourage you to play with this. This is an arbitrary member.csv. Again, that data is right here. And it's in a CSV file, which you could play with in Excel, and you could see how things change. So that is discrete naive Bayes classification with a training sample. Are there any questions? So I saw some in the chat. Let me get to that again. Okay. All right. Q&A. Okay. Yes, please go ahead, Parsa. Okay. And if you have to go and you have still questions, please feel free to email me. This will be available online. Okay. Okay. So yeah, in the interest of time, I will ask, because we're going to get through this next exam pretty quickly, and we'll have a couple of minutes for Q&A. So what I'll do is, in the interest of time, I will just go into this next example and we'll move on. So there was a question about actual numeric data. Well, we're going to get to that right now. Let me share my screen. Okay, so here is another application, diabetes prediction. Can these models be used to, say, predict diabetes in patients if we are provided with medical data? So what if numbers come into the picture, such as medical measurements? So I have this diabetes data set. This is also from that online book. The number of times the person was pregnant. This is a data set of women. Plasma glucose concentration, blood pressure, these other metrics as well. And we have finally at the very end, last column, whether or not the patient developed diabetes. So this is what the data set looks like. And I have it in a CSV file, and we're going to load it in R in a second. But this gives you a sense about what we're looking at now. Unlike what we had before, we are dealing with numbers. So what do we do? So we're going to have to utilize this concept called continuous probability distributions. The most common probability distribution is the normal distribution. This is also known as the Gaussian distribution, and it's a classic bell-shaped curve that occurs so naturally in nature. It is ascribed by two parameters, a mean and a standard deviation, or the latter is sometimes referred to as the variance when it's squared. And as you can see here, you have a variety of choices of means and standard deviations for plotting the normal distribution. And larger variances and standard deviations mean the data is more spread out. Smaller ones mean it's closer together. The normal distribution has this probability density function right here. And what people do is this, and I will tell you, I am not the biggest fan of this, but I will say that it works in many settings. So it's not, I guess it's not that unreasonable to do, but as a statistician, I have problems because it's technically not correct from a theoretical perspective. But what people do is they will take, just like we conditioned on the outcome variables for the discrete settings that we had talked about earlier, they will compute the mean standard deviation for the outcome variables, in this case, whether or not the person had diabetes, and compute the normal distribution, right, like this. For example, what is the mean and standard deviation of plasma glucose concentration for patients without diabetes? You can go through here and calculate the mean for these variables, because these are the people who didn't have diabetes, 99, 108, all the way to 105, and the standard deviation. And well, here I've computed the variance, and the square root is a standard deviation. You can compute these, and then you can this normal distribution with this mean and this variance will be what you use in your naive Bayes model for prediction regarding glucose concentration. This will be your equivalent of your conditional probability. And we're going to get to that in the example. And the idea is that what you will do is, suppose in your test data set, you get plasma glucose concentration to be 130. What you would do is you would plug into this probability density function, the 130, along with your mean and standard deviation, and that would be what you plug into your naive Bayes model. I am not the biggest fan of this from a theoretical perspective, because that is actually technically incorrect use of the normal distribution. Areas under the normal distribution curve elicit probabilities. The actual values of the PDF are meaningless. Nevertheless, people use them for naive Bayes modeling anyway. So I have an algorithm to predict whether a person has diabetes given factors doing that. And the code is written. So I will stop sharing my screen now. Before I get to the code, does anybody have any questions? Good question. How does naive Bayes compare to logistic regression-based classifier? It depends. That is a great question. And what one can do is test the accuracy. But the nice thing about naive Bayes is that it is much crisper to do. I had a problem that I'm working on with a friend at a semiconductor company in California, and logistic regression failed miserably, but the naive Bayes works very nicely. So it depends on the setting. So let me do this right now. I will share with you the codes. So basically, those probabilities, what we are doing now is plugging in to the normal density function. So this is our code here for the diabetes data, and I will show you the data set here. I just showed you on a snippet of it from in the PowerPoint, but this is what it looks like: number of times pregnant, plasma glucose concentration, blood pressure, and so forth. So what we do is we construct our training data set. This time I used 80%, but you guys are welcome to play with that. And I extract the diabetes categorization, which is the training data, the diabetes variable in the training data. Let me see it right here. I'll show you. This, oopsie, I dragged the wrong way. Yeah. Right here, it extracts this column, which is whether or not the person had diabetes. So what does it do? It, oopsie, it's right here. This is our code. This is iHealth. No, I'm sorry. PIMA-NB model _NB _ model. We go through this. We initialize mean and standard deviation matrices as well as the marginal probability, and we will go through the data set and compute the mean and standard deviation just as I had done in that slide for each category, whether or not the patient had diabetes for each variable in the data set. Then you have this, and you have the marginal probabilities as well. Those are computed the same way as before. Then you load your classifier function, which is right here, PIMA _ function. And it's basically the same rigmarole as before. You take in this loads into a row of your test data, which was constructed right here. The subsequent observation of the training sample onward to the rest of the data. And you got the mean, standard deviation, marginal probability here. And you go through your data, and we invoke the dnorm function in R, which is the probability density function, utilizing the pertinent mean and standard deviation. And then we also tag on the marginal probabilities into this probability test matrix. And we do exactly what we did before. We compute the product, and we use wish.max to figure which probability wins. And then we, at the very end, we return the probabilities as well as whether or not the model predicts the patient has diabetes. So that's done here. It goes one by one through the test data set, patient by patient. And again, we compute a percent accuracy by amalgamating what is predicted from the test data with what was assigned via the naive Bayes classification model. And how often are they the same? So let's do that right here. And this model has 72% accuracy. So despite the fact that it doesn't use the normal distribution properly, it's not that inaccurate, right? But you're using 80% of the data. You can see what happens if you bring it down to, say, 60%. %75% accuracy. So it actually goes up a little bit. So there's that. Now I have an example here with some hypothetical data. Here is, let me load this, Control Enter. Pima underscore example is the code, which you should have. And so here is the example data. Let me show you. I put two examples here. The patient was pregnant 4 times, plasma glucose concentration 105, and so forth. And then I had another patient here, pregnant 6 times, plasma glucose concentration 105, so forth. So how does this model predict? Let's find out. So I have applied it to the first row in that data set, namely this patient was pregnant 4 times. And let's see here. So these are the two probabilities. The former wins. So this patient is not assigned to have diabetes. It's not predicted that they have diabetes. How about the second one? That would be this patient that was pregnant 6 times and had a plasma glucose concentration of 154 and had blood pressure of 99. Let's do it right here. EX2. And in this case, the person is predicted to have diabetes based on the factors that were present. Okay, so those codes are available for you all to play with. You're more than welcome to play with them. And I encourage you to do so. So, are there any questions? You know what? I have, okay, let's do this. Are there any questions about what I presented? I have another concluding slide, which kind of casts panoptic gaze on everything. And then we can get into more general questions. We do have some time for that if you have any. I saw some in the Q&A. Oh, no, I think I answered. Good question. Should we check for normality in our training set? What should we do if our data is skewed? I encountered this very problem in something that I was working on. And yes, you cannot always use the normally distributed variable, random variable. So what I would suggest is plotting a histogram of your data and looking at the normality that way, and then seeing if it's not normal, are there any other distributions that are better fits? One choice could be, if it's skewed, maybe the gamma distribution, generalized gamma distribution, Weibull distribution, and so forth. And you could see. I have a paper that I am that will be coming out in a couple of weeks on naive Bayes classification, where we have tweaked the entire logic beyond just using density functions. Like I said, I'm not a big fan of that, but the application, I can't really say too much just yet, but the application of semiconductors does not really lend itself to plugging into the density function to begin with. So, any other questions?
Kevin, I saw one in the chat about, I think you were mentioning a book, and they were asking which online book are you referring to?
Oh, yes. Well, you know what? I can do that right now. Let me post the link right here. Ancient. Yes, and I almost forgot. Guide to datamining.com. And the chapter I structured this around was chapter 6. I tweaked it a little bit, but yeah, you are welcome to look at that. Are there any other questions? Okay, so let me conclude, and then what I will do is there might be some more general questions as a result of that. So firstly, I hope this was helpful. Now, like we've talked about, classifiers can be used to make product recommendations. We saw with T and Fitbit examples. You can classify items and people, such as voting, in terms of the congressional example, as well as the diabetes example, in terms of medical conditions. And there are many other applications ranging from spam detection, facial recognition, sentiment classification. Oh, I'm sorry, I'm not sharing my screen. I'm sharing it right now so you can see that. That's fine. From spam detection to facial recognition to sentiment classification. And there are some limitations about naive Bayes modeling. There are questions about the assumptions of statistical independence and legitimacy of that. You may not have the luxury of being able to assume statistical independence. The legitimacy of assumptions regarding normality and the necessary training sample for large data sets. If you are dealing with big data sets, then it might take a very, very long time to train your model. And then you have to think about things like parallel computing and efficiencies and so forth. So thank you. And I'm happy to take any questions now. And if you have any later, I'm happy to take them then.
Yeah, and let's just give it a minute because I know, typically people are typing out questions, so it might just take a second. Thanks, Anna. Thanks, Varish. Good to have you. Kind of while we wait to see if there's any questions, I'm just going to mention a couple of things. I've posted a link to our events page where you can find all of our events. And so next week on May 10th, we're going to be building a personalized attrition recommendation system. And on May 11th, we're going to be talking about the T-shaped data scientist and how going deep and broad can be the secret to your success. So a couple of events next week, and I think we have 2 events per week through July planned, which is kind of crazy to think about. So hoping to have you all back, and I'm still not seeing any questions. I would love to watch the replay so I can understand more of what was explained.
Somebody asked, how does naive Bayes take care of noise in the training set? So you don't. I mean, there could be noise in the data, and that is a limitation for any model, but you can get a sense of the accuracy using the techniques I talked about looking at the percent of correctly classified items. Yes, so that is really the best answer to that question. Okay. Go ahead, Nathan, I'm sorry.
Yeah, no problem. Laura, you were saying, please send those announcements with the slides. We definitely will send the slides when we email everyone. If you're on Zoom, odds are we have your email address, and we'll send you an email with the recording when it's available, and we'll attach the slides and everything with that. And are you teaching remotely or in person? We do it in a virtual instructor-led setting. So all of our courses are taught, I want to say in person, but they're in like over Zoom, kind of similar to what we're doing now, except for we give everybody a microphone and in camera and everything. I hope that answers that. And Laura, I sent you my email address if you want to email me and ask more questions about it.
Yeah, I'll put them in the chat too, my email address also.
All right, and I'm not seeing, I see a question on YouTube, Kevin. I'm going to post it in the chat for you. Maybe you can handle that one. It has to do with person being a little confused about the probabilities directly on the model or the model calculated from the data.
You put it
And
in
I
the
think
chat.
it's your example.
Where did you copy and paste it, Nathan?
Yeah, in the chat.
I don't think I see it. Oh, is it directly to me? Okay.
No, I sent it to everyone. I can send it to you if you'd like.
No. Oh, I gotta look. Oh, I see it. If you use the probabilities directly on the model or the model calculated in the data. Okay. So you take your training sample, and what you do is you compute the probabilities based on that. Then that goes into your test sample to test the accuracy of your model and subsequent data that you are testing. And in principle, when you're actually applying this in real life, your whole data set might be your original training sample, but you do want to see how accurate your model is.
And it looks like we have a couple other questions in the chat.
Okay. Yeah. So before using naive Bayes for facial recognition, is it necessary to do principal component analysis and an image segmentation through clustering analysis? There is a paper. Shoot me an email and I could send it to you. I have not had to do naive Bayes modeling for facial recognition, but I briefly looked at the paper, and I believe what they were doing was engaging in an image analysis, looking at pixels of various pictures. And I don't recall them doing a principal component analysis, but admittedly, I only had skimmed the paper. Oh, okay. So how does learning happen in the system? Good question. The idea is that you could update your training sample. So, for example, like I said, you may take 50% of your data for your original training sample, test on the remaining 50%. But the whole data set would be your original training sample when you're trying to make predictions. But then suppose you have more data a week later, you could use that as your training sample, so you have even more data. And that would make even more accurate, lend itself to even more accurate predictions the subsequent week, and so forth. Machine learning is a broad term. So the question is machine learning a technique in the traditional sense? Machine learning is a broad term, and this is considered an aspect of machine learning.
Okay, and I am going to cut us off there because we're about at our time, and I think people could probably keep you on and asking questions for another hour. So we're going to stop there. Thank you, Kevin, so much for coming and giving us this talk today. I'll make sure to we post the recording and everything anywhere and everywhere, so that if you want to watch the recording, it'll be there for you. Just again, we do have 2 events coming up next week, so give those a look. The slides will also be available. So thank you all so much. Thank you, Kevin. And I'm happy we were all able to learn something today.
Great. Thanks. Bye, Nathan.